This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing the topic overall heat transfer coefficient and cooling factor in heat and mass transfer subject. Here the main application of heat exchanger is it is exchange the heat from one liquid to another liquid when they are flowing parallel to each other or in counterflow or in cross flow. That is, it is extracted the heat from a higher temperature of the liquid to the lower temperature of the liquid by using certain separated valves. Maybe it is in the form of tubes or the valve. So the overall coefficient of overall heat transfer is given by the equations. Here Q is equal to U into A into delta T now, where U is the your overall heat transfer coefficient and Q is the amount of energy, heat energy that is transferred from the liquid which is having at a higher temperature to the liquid at lower temperature, and the delta T is representing the temperature difference between the two liquids now. The unit for overall heat transfer is same as the unit of convective heat transfer as well as the conductive heat transfer conduction. The thermal resistance incurred in heat transfer from one fluid to another fluid is shown in figure now. Here the thermal resistance now, here it may be due to the conduction process or convection resistance as well as the when the fluid is flowing through a pipe. Here that internally the scale is formed, this inner surface of the tube or the conductor, which is also prevent the heat transfer from the higher temperature fluid to the lower temperature fluid. That is the upper position also again now, because of forming scaling, the transfer of heat energy that is decreases because of forming at outer surface also. So the heat resistance which is increased at the inner as well as the outer surface of the tube because of forming some scaling is over the surface, inner the surface. That factor is called here now cooling factor. Here the resistance which are offered to flow the energy from the liquid which is having higher temperature to the liquid lower temperature, or one is the first convection resistance now. Here liquid is flowing, assume this is nothing but higher temperature. Here the liquid is there, outer temperature is having lower now. The heat energy has to flow from the inner to outer. First, the convection process is taking place to flow heat energy from the liquid to the inner surface of the tube now. So the heat convection resistance offered here is given by, so far the equation is Q is nothing but equal to H into, if you A is the unit H into A, here T1 minus T2 now. This equation it can be written as now T1 minus T2 divided by 1 by HA now. This 1 by HA is treated as that is convection resistance offered by the inner surface of the tube now. Similarly, here the scale is also formed at the inner surfaces now because of irregular maintenance not at all done according to the schedule. So the scaling also prevents the heat energy flow from higher temperature fluid to the lower temperature fluid now. So because of forming a deposit now, that is called here now scaling. The resistance due to the deposit that will form during the operation on inside of the tube is called inside fouling resistance. Generally it is represented as RFO I now. After that, from the tube it is there now, it is having certain wall thickness. The heat energy flows from the inner surface to outer surface. That is, if we represented like this, again by using the conduction process. So the heat energy which flows by the conduction process is given by K into A into T1 minus T2 divided by here L now. That means the amount of energy that is flowing from one point to another point is proportional to the thermal conductivity and surface area and the temperature difference T1 minus T2 and inversely proportional to the thickness now. So it can be written as now T1 minus T2 divided by L by K into A now. This L by K is called thermal resistance, which is offered by the body when the energy is flowing by using conduction process. So this resistance is called here now conduction resistance. So the resistance due to the conductions. It is there. Now again the resistance which is obtained because of forming this one layer over the surface of the tube, that is called this outside fouling factor. That is resistance due to the deposit that will form during the operation on the outside of the wall of the tube is called outside fouling resistance. Though the convection resistance from outside to again the liquid is there which is surrounding outside of the tube. That is our aim is transforming energy from the fluid which is in the tube to the fluid which is outside of the tube now. Hence, here the transfer of energy from the outer surface of the tube to the liquid which is surrounded over the tube is given by again convection process, which is given by 1 by H naught to A naught. So the total resistance is equal to sum of the resistance offered to the liquid to flow the energy. One is the convection process from the inner to surface. The second one is the fouling resistance. Third one is the conduction resistance. Again, just fouling resistance. This, if you take sum of all this resistance, this is called here the resistance offered by the system when the heat energy flowing from inner, from the hot fluid to the cold fluid which is surrounding outside of the tube. So the total resistance it can be calculated by using the relations now. 1 by U I A I. This is nothing but representing U I is nothing but just overall resistance is given. A I, this 1 by U I A I is equal to that is overall resistance, thermal resistance, which is equal to now 1 by U naught A naught. Both are equal because the amount of heat energy that is flowing from inside to outside is the constant now. So both should be equal only. Or from this relation we can write to U I A I is nothing but equal to U naught A naught. Both are equal now. So which is equal to the resistance offered here now 1 by H naught A naught and is given. This is called convection resistance. The second one is here fouling resistance per unit area, that is A naught. Here one more is there now, here RK, that is the resistance offered due to the conduction process. Again one more is fouling again factor, the fouling resistance at the outside of the tube. Again convection process 1 by HI A I now, that is nothing but at the outside now. So here the total resistance since here 1 by U naught when we are taking now. So on doing the calculation, that is we got to 1 by H naught, that is A nothing but common factor when you taken RF naught, A naught to RK plus A naught divided by AI into RFI, A naught divided by A into 1 by HI now. So this is known as this overall resistance offered by the system when the fluid is flowing from the inside to outside of the tube now. Okay, for the pipes, it can be written as now internal and outside now 1 by UI is equal to AI into A naught. When we are taking this pipe we are taken, we can write it like this now. Here the fouling factor is a parameter used in a design and analysis of heat exchanger to account for the expected build of unwanted materials. Because when we are designing or the manufacturing any heat exchanger, the main purpose of heat exchanger is you are transferring the heat energy from one fluid to the another fluid. When the fluids are flowing maybe in parallel or in opposite directions, that is, or it may be cross, counter flow or parallel flow or the cross flow. But here, when the because of forming that fouling on inner side as well as the outer side, the heat transfer rate that is the decreases. Hence, according to the manual, some regular maintenance is required. It may be depending upon the number of hours it is working, type of the materials that is used while doing the constructions. So, but in between, because of forming that scale, because even though just we are removing that scaling at regular intervals, the account of heat transfer due to the fouling factor is to be considered while designing a heat exchangers. So the build-up that is known as here now fouling can significantly impair the performance of the heat exchangers. When thickness of the fouling is more, that is the performance of the heat exchanger decreases. The fouling factor provides way of quantify this effect. The fouling factor RF is defined as the additional thermal resistance expressed in terms of meter square per degree Kelvin per watt because of forming unwanted layer inside as well as the outside of the tube. So the total resistance of heat exchanger with the fouling can be expressed as RE total nothing but total resistance, which is equal to the sum of the resistance offered by the tube when it is in clean now. That is to put it in operations or after the regular maintenance plus RF that is equal to fouling factor. It can be represented as now 1 by UF minus 1 by UC now. The overall heat transfer coefficient U of a heat exchanger with the fouling can be related to the clean overall heat transfer coefficient U clean as follows. That is 1 by U is equal to 1 by U clean plus here fouling factor RF, where U is representing overall heat transfer coefficient including the effect of fouling, and U clean is representing overall heat transfer coefficient when the heat exchanger is in clean, that is when it is installed at that moment or after regular maintenance. Immediately the resistance which is offered to the heat energy flowing from inner to outside is called here U clean. In practice, the fouling factor is determined based on the empirical data and experience with the similar system of fluids. Generally, this data is supplied by the manufacturer after giving certain regular intervals for the maintenance. That is the maximum resistance that is offered. The heat exchanger can maintain acceptable performance over its operational life despite the expected fouling. The fouling factors are provided in engineering references depending on type of the fluid or operating conditions or material construction of heat exchangers. This value is changing depending on type of the fluid which is flowing inside it also. The regular maintenance and cleaning schedules are often implemented to manage fouling so that the efficiency of the exchanger can increase or maintains almost uniform. Okay, based on the fouling factor, just we are having one problem now. In a condenser steam flows outside the tubes of radius 59 mm and 54 mm and seawater flows inside the tubes. The thermal conductivity of the tube metal is 60 watts per meter per degree Kelvin. The steam and water temperatures are below 50 degrees centigrades. The convection coefficient on the steam side is 12,000 watts per meter square per degree Kelvin, and the value of water side is 650 watts per meter square Kelvin now. Calculate the values of overall efficiencies based on the inside and outside areas. Also determine the percentage of error involved in neglecting conduction resistance, fouling on the side and outside conductions, and considering only the water resistance. From the tabulated values, the fouling factors are read as for the sea water below 52 degrees centigrade, its value is equal to 0.0000877 kilometer square per Kelvin, degree Kelvin meter square per watts. For the steam, it is given again now 0.0000877. Using the equations here now, the overall heat resistance is equal to 1 by U naught is equal to the sum of the resistance offered by the first convection process. The second one is the fouling factor inside conduction process. Afterwards again fouling factor effect, fouling resistance and the convection process. You have to take it. So from this relationship we got to here 1 by 12,000 it is given now plus 0.00087 0.059 into login of 59 divided by 54 divided by 60 plus 0.059 into 0.04 multiplied by again fouling factor 0.0000877 plus 0.05 divided by 0.054 into 1 by 650 now. So this is nothing but based on the equation 2a, substitute the values. We got from these relations now 1 by U naught, that is the overall resistance is equal to even 49 is equal to, and doing the calculations, U naught is equal to, that is overall thermal conductivity is given by 491.44 watts per meter square K now. Overall coefficient of heat transfer. In this case, it may be noted that all the resistance other than due to the inside convection coefficient are 2 orders of magnitude is lower. So leaving the conduction resistance now, we got U naught is equal to 513.40 watts per meter square per degree Kelvin. It is approximately the percentage is 4.47%. Again, neglecting the outfalling and conduction resistance, the overall coefficient of heat transfer is given by U naught is equal to 566.8 watts per meter square per degree Kelvin. So the percentage of change is 15.4 now. Considering only water side resistance, U naught is equal to 594.88 watts per meter square per degree Kelvin. So the percent of change is 21% now. In this case, the water side resistance is controlling as it forms 80% of the total resistance now. The overall heat transfer coefficient based on inside area is equal to, because the heat energy which is flowing through the pipe is remains constant, that is here Q is equal to, we can write it U naught A naught here T1 minus T2, which is also equal to U I A I T1 minus T2. By using these two relations 1 and 2 now, we got U naught A naught is equal to U I into A I now, which is given here the expression is. From these relations now, U naught, A is nothing but equal to the surface area, which is equal to 2 pi r naught into L, which is equal to Ui into 2 pi r I L now. That is nothing but where r naught representing this inside radius of the wall and I naught is representing outside radius now. So Ui is equal to U naught r naught divided by Ri, which is equal to 536.94 watts per meter square per degree Kelvin. The value is higher in proportion to the area ratio. Okay, these are the textbooks referred for collection of material, particularly the fouling factor as well as the problems based on it. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.